we're going to be talking about domestic robots. So we're going to do a multidisciplinary engineering analysis of household robots. So without further ado, what are household robots? So domestic robots do tasks around the house, such as cooking, cleaning, folding clothes. They do essentially just the everyday task. But these simple everyday tasks can involve extremely complicated engineering and development. So we're going to mostly focus on the main aspects, which are electrical, mechanical, software, and computer engineering. Now, I will begin by focusing on the software and computer engineering aspects. But first, a lot of companies are pushing the bounds of research and development in these fields of domestic robots. For instance, Boston Dynamics are a really popular group, and they worked on robots that are extremely efficient, extremely intelligent. So without further ado, software and computer engineering. So, what are the main fields of research for software and computer engineering in terms of domestic robots? Well, they work on perception, robotics, artificial intelligence, and machine learning. So what we see in this diagram on the right, this is an architectural design pattern for these robots. So the hardware linked to perception is going to be able to collect data that is going to be piped into the control software. The control software will then choose an action to do which will modify the environment and therefore change the perception, kind of working in a cycle. And that's how these robots are kind of built, most of them. So let me get into a little more detail about perception. So these robots use what's called as cognitive perception and semantic mapping. So what is this? This is basically the robot is able to see objects and to actually think of what they are and how they are used. So this is really fascinating. So these robots are built with the goal of developing a robotic system with a high degree of cognition. The goal is driving research in 3D perception, cognitive control, knowledge processing, and high-level planning. So important features of these robots are spatial knowledge about the world, so position of obstacles, ontological knowledge about objects, their types, relations, and properties, just common sense knowledge. So for instance, if an object's inside a cupboard, they're not visible from outside unless the door is open. And knowledge about the functions of objects. Like if it wants to operate a dishwasher, well, it's going to recognize that it's a dishwasher, and then it's going to know which sequence of actions is required to operate the dishwasher. So some of these robots actually use their own programming language, such as for this one, this is a robot that was developed in Munich by TU Munich. It uses the CRAM software language. It provides a language for programming cognitive control systems. And the goal of CRAM is to allow autonomous robots to infer decisions rather than just having pre-programmed decisions. This approach will enable tackling of the complete pick-and-place housework cycle. And this can do a lot of basic tasks with this programming language. So to get into more detail about why it's better to infer decisions than having pre-programmed decisions, well, that is called actually machine learning. So robots teach themselves to grow as they're exposed to new data rather than explicitly programming each task. So as we can see here on the right, the robot's getting up by itself. So instead of programming a function that's going to tell the robot to get up, so you're going to need the get up function for each different robot. But instead of programming this function for each robot because their physical architecture is different, you can just have one function that's going to work for every robot. And this function is actually going to allow the robot to get up multiple times until it figures out how to do it. Really fascinating. So what is the impact of this research on the fields of software and computer engineering? Well, machine learning is useful outside of robotics, like in finance and statistics. It can push the bounds of processor performance, find energy-efficient solutions, and develop fields of computer vision. Finally, the impacts on society. Save time. This is a no-brainer. Not having to do all of these household tasks can save a lot of time, but that's not the only reason why. You don't want just some fancy robot folding your clothes. These can actually be used to help people with disabilities. That is a big field. Like a lot of nurses have to take care of people. Being able to replace them with robots can be really grateful. It is safer and They can do work in practical facilities as well. Now, without further ado, to get into more details about the mechanical and electrical aspects of robotics, I'm going to let my colleague talk right now.
The branch of mechanical engineering and electrical engineering deals with the construction, design, and embedded system of robots. Robots all have some kind of mechanical construction, a frame, form, or a shape designed to achieve a particular task. For example, a robot designed to travel across a heavy dirt or mud might use caterpillar tracks. Robots are required to have high mobility and dexterity to work in large reachable range and variety of workspaces. It is parallel with the mechanical structure of a human arm which give them these properties as you can see in the slide. Locking mechanism of a strand beast is shown here in the slide. It consists of a caterpillar beams forming a sequence of link and membranes. It is very efficient in rough terrain and in underwater robotics and also in domestic robots. The electric aspect of the robot is used for the movement through motors and remote sensing, which is very important, and where electrical signals are used to measure things like heat, sound, position, and energy status and operation. I cannot stress enough the importance of this branch of the robotics, which is remote sensing, in the efficient working of the robot. From what proceeds, the role of the mechanical engineering and the electrical engineer in robotics appear to be at least important at these three levels. Multidisciplinary aspect of the robotics, let us note that the mechanical and electrical structure of robot is only the visible part of iceberg. Robotics is essentially a multidisciplinary field in which engineers from various horizons such as electrical, mechanical, software, computer play equally important roles. By looking at the above rules, we can comprehend that the basic goal of the robotic mechanics, dynamics and electrics is twofold: to extend our understanding about manipulation and locomotion of the robotic behavior, to develop engineering methodologies to actually perform desired tasks. Many of these applications entail some locomotive functionality so that robot can freely move around in an unstructured environment. Combining leg mechanism with wheel has accomplished superior performance in both efficiency and flexibility. As you can see, the Mars rover prototype shown here has a rocker buggy mechanism combined with advanced wheel rise in order to adapt itself to diverse terrain conditions and at extreme temperatures. Although wheel robots are typically quite energy efficient and simple to control, other form of locomotion may be more appropriate for a number of reasons. Example in moving and interacting in human environment. A major goal of the in this field is developing capabilities for robots to autonomously decide how, when, and where to move. As you can see, the robot Marlow here. The second is the robot manipulation, a collective name for all sorts of mechanism for performing a class of tasks. A robot mechanism is a multi-body system with multiple bodies connected together. Each ready body is involved in the robot mechanics is called a link. There are two types of link, as you can show in the as you can see in the next slide. In this, the robot Marlow is very simple to control, and it's the bot technology which has versatile prosthetics which makes it very easy to move in rough and terrain conditions. These are the type of joints. One is sliding joint and the other is rotating joint. This type of joint is often referred to as hinge or rotational joint. Combining only these type of primitive joints, we can create many useful mechanisms for robot manipulation. Most of the robots that have been built are combination of only these two types. The mechanical structure of the robot manipulation may be regarded as a multi-body system, a system of bodies, links, rigid in theory. Whatever the function assigned to it, like handling, painting, assembling, welding, a robot manipulator is designed mechanically to locate in space a tool often called effector. The geometric location of the effector is generally quite arbitrary in the reachable range called the workspace of a manipulator. Thus, how you can see that how the manipulator is important in functioning of the robot. For instance, in this slide, I'm talking about a robot Atlas, a 6 feet bipedal humanoid robot. It is made by Boston Dynamics. Atlas is a high mobility humanoid robot designed to negotiate outdoors rough terrain. Atlas can walk bipedally, leaving the upper limbs free to lift, carry, and manipulate the environment in extremely challenging terrain. Atlas is strong and coordinate enough to climb using hands and feet to pick its way through congested space. Articulate sensate hands will enable Atlas to use tools designed for human use. Atlas includes 28 hydraulically actuated degrees of freedom to hands, arms, legs, and torso. Atlas is powered from an off-board electrical power supply via flexible tether. The manipulation in Atlas robot is designed to operate outdoors and inside buildings. It is electrically powered by the automated embedded systems and hydraulically actuated. It uses sensor in its body and legs to balance and leader the stereo in its head to avoid obstacle, assess the terrain, and help with navigation. If the folks at Boston Dynamics have attained what it took evolution nearly 500 million years to accomplish, one can only speculate how far they will push the bar in the next few decades to come. Mechanical and electrical engineering students learn how to approach a problem, generate solution, and evaluate solution and support their decision with mechanical structures. An airplane is essentially a robot. The autopilot can control the plane for each stage of generally including takeoff, normal flight, and even landing. This level of integration requires the interdisciplinary knowledge, which is the strength of those trained in robotics or more broadly in mechanical, electrical, computer, and software engineering.